Hi. So this particular video is going to be about waves and sound. So we will cover largely some basics about waves, wave pulses, and periodic waves. Sound comes a little later on in the chapter that we're walking through right now. So this will be just about waves to give us an intro. All right, so what is a wave? Well, we can think of a wave as a traveling disturbance that carries energy from one place to another. Typically, a wave is going to require a medium to travel in. The example we've got from the figure there is a wave on a spring, and that spring acts as the medium that the wave travels down. We could think of, let's see, maybe a long piece of string, and we could send waves down the string, and so that could be a medium. Let's see, what else? What other kind of waves could we have? Sound waves. Typically, we think of sound waves as traveling through air, so air acts as the medium for sound waves. Sound can also travel through liquids and solids too. It's just normally we think about them traveling through air. But yeah, that liquid or a solid could act as a medium for sound waves as well. Let's see, what other kind of waves are there? Water waves, okay, and so definitely the medium there is water that the waves travel in. There's also electromagnetic waves, which actually kind of act like their own medium, don't really require a medium, a separate medium to travel through. That comes, that whole topic of a medium for electromagnetic waves for light. We'll talk about that much later into this particular course than right now. So we'll maybe save that topic for a later date. All right, so focusing in again on the figures that are on the screen here. What we notice is that individual pieces of the medium will oscillate back and forth about their equilibrium position. So for instance, if I focus in on maybe this particular spring right there, that particular spring does not travel to the right. It doesn't. What does it do? It just kind of moves down, and then it's going to move back up again, and so on and so forth. So maybe I picked a bad spot. Maybe I should have picked this spot right here, where now this thing is moving down. It's moved down, and then it's going to move back up again. And that's what the figure tries to show there, that individual piece of spring at any horizontal position along this wave is just oscillating up and down. It's not traveling to the right with the wave. All right. So the figure that we have here is what's called a transverse wave. We'll talk about that more here in just a moment. Okay. But a wave is a traveling disturbance that carries energy from one place to another. All right. What we have here is an example of something called a longitudinal wave. So this is, we can see our wave here is traveling to the right. Let's see, our wave here is traveling to the right. And our individual pieces of spring are also moving, oscillating right and left. So it's like our medium is moving in the same general direction as our wave is traveling. So our wave is traveling horizontally, and the motion of our individual bits of spring is also horizontal. It's left and right. So if we've got a longitudinal wave, that means that my medium is oscillating parallel to the direction of the wave. All right. So let's take another look at that transverse wave real quick. So there's our transverse wave. And this time, instead of my medium oscillating in the same direction as the wave is traveling, our medium is oscillating perpendicular to the direction of motion of the wave. So here we can see that the wave is traveling to the right. as time continues on. And then what's this individual piece of the medium doing? It's oscillating up and down. It's oscillating perpendicular to the direction of the wave. Okay, so that's what transverse means there. All right. Transverse means that our medium is oscillating perpendicular to the direction of the wave travel. Okay, let's see here. Need to go back and erase my figures. Sorry about that. It's been a little bit since I've used that functionality on Zoom. All right, so if we've got water waves are actually a combination of transverse and longitudinal waves. So this individual water molecule that we have highlighted here, right there, will actually not just travel up and down. That would be transverse to the direction of the wave. Nor does it travel just back and forth. That would be longitudinal with respect to the wave. But instead, it has a combination of transverse and longitudinal motion, which is what we've tried to highlight out here with this this circular path that's drawn. So that little piece of medium still is oscillating about an equilibrium position, right smack in the middle, right there of that circle. It's not traveling to the right with the water wave, but its motion is a combination of transverse and longitudinal motion. So water waves are partially transverse and partially longitudinal. All right, so let's see what's next here. I have a question for us. It says we've got a transverse wave traveling along a slinky. Okay, this drawing shows, let's see, the slinky at one instant in time. So this is just the slinky at one instant in time, this black line that we've got drawn there. The wave is going to travel to the right. Okay, so we can imagine the position of this wave, I don't know, 1/10 of a second later as it travels to the right. We've got two segments that are highlighted on this slinky. It's segment A and segment B. Okay. And it says at the instance shown, which of the following statements correctly describes the motion of the particles that compose the slinky in segments A and B? All right, so let me pull my little thing up there. There we go. So I'm focusing in on segment A there and segment B there. And so choice A says, well, in segment A, the particles are moving downwards. In segment B, the particles are moving upwards. In choice B, it's a different combination of those two things. Choice C, choice D, so on and so forth. I would ask that you pause the video here, that you read through the selections, and that you try to make a choice about what this segment A and segment B are doing as this wave travels to the right in the next instant shown. Okay. So pause the video. Okay, so let's see if we can answer this question. So in order to answer this question, what I've done here is I've done my best to draw the wave, you know, again. So I've got it basically the black line there traced in red. And what I'm going to do next is I'm going to allow a little bit of time to elapse. I'm going to let that wave travel to the right. So let's do that. All right, so my wave now has traveled to the right. It has moved from the position where it was before in black, now to the position where it is in red. And now let's see, well, let me change colors here real quick. Let's see what's happened to this segment at A. Whoops, I missed. So that's segment at A. So all of those coils, all of those pieces of my slinky that make up segment A, which is in between those two black dots, have moved upwards. So they've moved from the position they had before on the black line to the new position they have on the red line. So segment A has moved upwards. So let's see, segment A has moved upwards. So those two are possibilities now. Well, what about segment B? Okay, and again, keep in mind that I'm doing my best with crude drawings, so on and so forth. But it looks like segment B, the piece of the spring that makes up segment B, has traveled from where it was before on the black line downwards to now where it is on the red line. So that part that makes up B has moved downwards. And so let's see, B moves downwards. And so it looks, let's see, I've got a B moves downwards there. Of course, I don't have the A highlighted. It looks like the only choice that it's appropriate here that has both the particles for segment A moving upwards and the particles for segment B moving downwards would be choice D. And choice D is in fact the right answer, okay, which we'll see here in just a second. There we go, choice D, yeah. All right, so let's see what's next here. All right, typically when we think of waves, we think of a periodic wave, a wave that repeats itself over and over and over again. We don't have to have periodic waves. We can have wave pulses, and we can talk about that. Yeah, I want to focus on periodic waves right now. So our periodic waves consist of a bunch of cycles that repeat over and over again. If you look at the figures, then especially our little let's see, our little red dot right there. Maybe yellow is not the best choice. Our little red dot right there. There we go. Our little red dot is actually moving in simple harmonic motion. That means as it oscillates up and down, if we were to make a graph of its motion, what we would see, and so if we were to make a graph of the motion of that little red dot, and if we were to graph its height, its position in y versus time, then what we would generate is basically a sine or a cosine wave. So something like that. Doing the best I can, drawing with my finger. So this is like a graph of my little red dot there. So this is a graph for my red dot. Okay, that's one kind of graph I can make for this wave. The other kind of graph I can make for this wave is just by taking a picture of it. Okay, so if I take a picture of this wave right here, well, a picture of that wave would look like a picture of that wave. Okay, fine. Let's see, what's this look like? Something like this. What have I got there? I've got the y position of my individual coils of spring versus x. So yeah, I've got their vertical position versus the horizontal position. Okay, so there's two different kinds of graphs I can make for a wave. I can make a snapshot graph, a y versus x graph, or I can track out the motion of one individual piece of the medium. So this would be my y versus t graph for this transverse wave. Okay. What if I were to make the same kinds of graphs for my longitudinal wave? Well, the only difference really in terms of the graph that I've got on the right-hand side, one second, would be that instead of having a y there, I would have an, there we go, I would have an x, okay. So if I were to graph out this guy here, I can very easily graph out the position of that red dot there, except now along my vertical axis, I would have its position in the x direction versus time. But then in terms of my snapshot graph, this one over here, it's a little harder, actually a lot harder to visualize what that looks like. So we'll, as we make these graphs, maybe it's a better idea just to stick with kind of that type of motion, transverse motion for a wave. All right. Okay, so I've got my two graphs here. On the left-hand side, I've got my snapshot graph, my picture graph. On the right-hand side, I've got my vertical position versus time graph, my vertical position for my little red dot. Okay. You notice that in each one of these graphs, there is a bit of the graph that's highlighted in color, so it's shaded in color. Those shadings show one full cycle for my wave. For my left-hand graph, this full cycle corresponds with the wavelength of the wave. That's basically how far my wave travels in one full cycle. On the right-hand graph, this is my little red dot moving up and down. One full cycle corresponds with the amount of time it takes for my little red dot to move up and down. Okay. That time has a specific name. It's called the period. The period is the time for one complete cycle. The amount of complete cycles that I have per second is called the frequency. Okay, so I can find the frequency by just taking 1 and dividing it by the period. That's the equation that I've got down on the bottom there. The frequency is the number of cycles that I have in each second. Okay, so the number of waves that I have in each second. The number of times this thing oscillates up and down each second would be the frequency of the wave. All right. There's one other thing that I want to highlight here, and that's the amplitude. So let me grab my little drawing tool. A little drawing tool there. There we go. Okay. So the amplitude is the maximum displacement of a particle from the particle's equilibrium position. Okay. So we've got here the amplitude right there and the amplitude right there. That is basically, let's see, our equilibrium position for our slinky, if it's all strung all the way out, would just be the x-axis. And then as the individual pieces vibrate up and down, the largest distance they get away from that x-axis is what's called the amplitude of my wave. Okay. And that amplitude shows up both on my snapshot graph and also my position versus time graph over here. You can see that I've got amplitude and amplitude there. So my individual little red dot is at its equilibrium position. It goes all the way up to its peak and then all the way back down to its trough and then back to equilibrium position. So that peak, distance from the equilibrium position to the peak would be the amplitude. The distance from the equilibrium position to the trough would also be the amplitude. And so I could look at either one of those on a graph to get my amplitude for my wave. Let's see what's next here. All right, so I've got a question for us. It says we've got a drawing of a wave on a string. So this is a transverse wave. And we've got 6 points highlighted there, points A, B, C, D, E, and F. And it asks between which 2 points is the length of the segment equal to 1 wavelength. So I would ask that you pause the video and get an answer. So pause. Okay. So the correct answer here is that if I go from A, whoops, sorry, I needed to grab my tool, which I did not do. If I go from A to E there, I've gone through 1 full cycle of my wave. So I've gone from peak to peak. Let's see, is that the only option that I've got among the ones listed? Yes, it is. Is that the only full wavelength that I can pick out on my graph? No, it's not. I could also look at from B to F there. That would be 1 full cycle. When I start at B, I'm starting, let's see, I'm going from, let's see, above the x-axis to below the x-axis. And then I'm going below the x-axis, I hit my trough. Now I'm going up above the x-axis. I hit my peak. And then when I get to F, I'm going now again below my x-axis. That's 1 full cycle of motion there. So from B to F would be a wavelength as well. So wavelength is represented with lambda there, which we saw in the previous slide. All right. So here's another one. We've got a continuous longitudinal wave. Remember what a longitudinal wave is. A longitudinal wave is is a wave that has its medium oscillating back and forth along the same direction that the wave travels. So we can picture a slinky that's all stretched out, and we kind of shoved it. Instead of moving it up and down, we kind of shoved it. We're shoving it like this and causing oscillations all down its length, to travel all down its length. Okay. So we've got a continuous longitudinal wave that has an amplitude of 0.02 meters, moves horizontally along a slinky. The wave speed is 2 meters per second. And we're asked which of the following statements concerning this wave must be true. Well, is it each, and I'll let you read those, pause the video, and see if you can come up with a response. So pause. All right. So this is a little bit tricky to think about. And in an effort to help us think about this, I'm actually going to try to draw out here kind of a mock-up of a slinky. So we've got like a slinky right here. There we go. Doing my best. The wave is traveling to the right there at some speed v. Okay. And we can focus in here on maybe an individual piece of the slinky there. And that piece of the slinky is going to be oscillating right and left. So this thing is oscillating right and left. Why? Because it's a longitudinal wave. And in a longitudinal wave, the disturbance travels along the same direction as my wave travels. So the oscillation is parallel to the velocity of my wave. All right, let's take a look and see if we can figure out how far this individual dot, this individual piece of spring that I've got marked out there, travels in one cycle. Okay, so let's see. It starts out right at its equilibrium position, and it travels to the right. It travels to the right the distance of its amplitude. Okay, so the amplitude is the maximum displacement away from equilibrium. So it travels 0.02 meters. All right. So it gets to that maximum distance, and then what happens? Well, it heads back in the other direction. It heads back in the other direction until it travels all the way to the amplitude, the maximum displacement in the negative direction. All right. Well, how far has it traveled there in that bottom arrow? Well, it's traveled a distance of twice the amplitude, 0.04 meters. All right. Now, to complete the cycle of its motion, it has to travel from there back to its equilibrium position. And how far is that? That is 0.02 meters. So if I add up all these distances up that this individual spring, this individual coil has traveled in one cycle, I get 0.02 plus 0.02 plus 0.04. That gives me 0.08 meters worth of travel for this coil. So it's traveled 0.08 meters. And in what direction? Well, let's see, my slinky was horizontal, and this is a longitudinal wave. So this coil, or this particle, is going to travel in the horizontal direction. So the correct choice here is C. We don't know how far it travels in each second. We don't have enough information, honestly. If we knew maybe the wavelength of our wave, then maybe we could figure out the distance traveled. If we knew the frequency of our wave, then maybe we could figure out the distance traveled. But we just don't have enough information to determine if A is correct or not. But C is definitely correct, and our question there said which must be true. So C is the correct answer. All right, so I am going to give us a little break and stop this here, and we will pick up our discussion again on the next video.